Okay, so good afternoon, everybody. My name is Bruno Mundin. I hope you can hear me well. Please let us know right away so we can try to solve any technical problems with sound. You can ask questions in the chat. You can see the chat on your screen. And today's attendance code is 10. If you have any questions, my colleagues, Faye and Yohai, will help answer the questions. The format of this lecture, of today's lecture, is a little bit faster paced than in the workshop, but we are going to have time to go back on these problems, on the code, and I encourage you to look at them as well. So, as I said, my name is Bruno Mundin, and I work for SciNet. I'm an analyst there. And today we're going to talk about parallel programming at scale on supercomputers with message passing interface, or MPI for short. Okay, so first I will refresh our memory on distributed memory computing, and then I will follow along with the basics of MPI, some basic concepts like communicator, message, MPI task, or MPI process, right? And then we're going to move on to MPI send and receive, where these MPI tasks actually send messages to each other. And this is a kind of a communication that happens between two tasks only. And after that, we're going to talk a little bit about collectives. That those are communications that happen when all the tasks, all the processes involved in the MPI communicate with each other. And finally, I'm going to finish today introducing a scientific MPI example that is one-dimensional diffusion equation. And I'll leave you with a problem to parallelize that one-dimensional diffusion equation. I hope you enjoyed that problem. It's quite fun. Okay, let's see on distributed memory computing. So whenever okay, the kind of systems, HPC or supercomputer systems that we have out there is quite we have quite a lot of options. You have seen you have worked with programming on the shared memory machines, for example, the symmetric multiprocessor machine. Those machines, all the processes, they share the same memory, and it's typically a limited number of cores. And those were the first supercomputer machines, one of the first supercomputer machines. And as the engineers, they tried to increase the number of cores, it became more and more complex to manage that. And eventually, what happened was they decided to, in order to parallelize their programs, in order to build a machine that would allow you to run parallel programs, they decided to just connect a bunch of servers together in a network. And that's how the distributed memory machines were born. So nowadays you have all different kinds of interconnects. For example, GigE, there is a slower one, InfiniBand, that we have on our systems at SciNet, on Teach Cluster, NIST, and Niagara. You have Cray interconnects and the late IBM BGQ Taurus. Also, in the past, the granddaddy of all these machines used in HPC, in high-performance computers or supercomputers, right, is the vector machines. Those vector machines were machines that would do computation on a very large vector of data at the same time. They are no longer dominant in high-performance computing anymore, but we still have a niche that is useful. And the main developers nowadays, the main players are the Cray and NAC. Ramses mentioned quickly about the accelerators, that you basically have a very specialized processor like a GPU or cell or NIC or FPGA, the field programmable gate array, that you connect to your motherboard, and then you try to program those to accelerate the computation of your code, right? And the main players are NVIDIA and AMD, as you already know, Intel, and Xilinx and Altera. And of course, you have the hybrid architecture that is basically most modern HPC clusters nowadays, that is going to be a combination of the above. So for example, our cluster Niagara will have, it's a cluster of, it's a machine of a distributed memory machines, but at the same time, each compute node is also a shared memory machine. And at the same time, each process has some vector capabilities, some vector units in the chips that you can still explore. While our other machine called MIST do have a GPU accelerator. Okay, so that's how the modern. And why the distributed memory machines are so appealing? It's because it's simple to build, right? You basically take existing powerful standalone computers, as you can see these modern exemplars here on the left, and then you just connect them with a bunch of cable, and there you go. You have a distributed memory machine, okay? What are the main features of this distributed machine? As you can infer, each node is independent. So each node will have their own CPUs and their own memory. It could be a shared memory system as well on each of these nodes, but not necessarily. Nowadays, it is as a de facto standard. So, and you use the codes to run on each of these compute nodes, okay? And they communicate with each other by sending messages between them. So here, as a notation, this is the memory of each CPU, of each node, and then here represent a CPU, or if you want to talk about a more modern architecture, a core inside of that node. So you could run different programs on each of these CPUs, but you could run the same instance on each of these CPUs as well. And if they need, so suppose that you're doing some computations on a matrix, right? The CPU one is computing on the row, on the first row, and the CPU two is compute on the second row. And all of a sudden, if you need data, if the CPU one needs data that is on the CPU two, the two of them needs to talk to each other, and the CPU two needs to send some data to CPU one in order to process. Okay, so you don't have a direct access on this model to the memory on the other compute node. The memory is exclusive for each compute node. So as I said, in terms of the hardware, it's very easy to build. It's hard, of course, to build well. That's the reason that we have several vendors try to compete when we build a new system. And it's very easy to extend. For example, Niagara just recently was extended from 60,000 cores to roughly 86,000 cores. But the drawback of this kind of system is that the communication needs to be hand-coded. So you need to tell explicitly on each CPU, on each code, on each program that is executing, how they're going to communicate with each other. So with these different kind of compute architectures, it's obvious that you're going to have different kind of programming models, right? So the first one that we saw on the introduction to HPC was basically when you have a serial code just compiled with the usual C, C++, or Fortran languages, right? Or more recently, Julia, or maybe it's just a Bash script or Python script, as was the problem that you solved on the first lecture, in the first week. And then you just want to run that several instances of that serial code, right? So those are the so-called embarrassingly parallel applications. They basically don't need to communicate with each other, and it can be easily parallelizable, and you can exploit shared memory cluster, shared memory machine by sending out several of these instances on several different nodes, And that was what you did with a GNU parallel in the first week. And of course, if you want your application to explore the shared memory inside each compute node, so you need to thread your application, and you can do that either with OpenMP and P threads, and then you have some experience last week or 2 weeks ago with OpenMP. And today we're going to talk about message passing. That is the programming model most used in distributed memory machines. And that's the standard, the de facto standard is the MPI. It's the most common used one. Of course, we have other models like partitioning global address space. That is the basis for UPC. That is an extension of the C language and the base of co-array Fortran that is now part of the Fortran language. And those are other possible ways to explore parallelism in a distributed memory system. And of course, accelerators, you're going to need more specialized languages like CUDA, OpenCL, and OpenCC, which we are not going to talk today. And of course, we have the hybrid combinations of the above. For example, it's very common on Niagara to use MPI and OpenMP at the same time, MPI to distribute the jobs across the several different nodes, the tasks across several different nodes, and the OpenMP to explore the parallelism on the different cores inside each node. We're going to focus today on MPI. Okay. Also, these programming modes that I just mentioned, they will also depend on what kind of task that you have at hand. For example, or what kind of algorithm, what kind of problem you have at hand. So if you have a computational bound problem at your hands, so you need to take the work to be done and decompose that across the processes. You're going to employ what is called the task parallelism. You basically will divide and conquer. Each process is going to be responsible for some part of the algorithm. The communication will be significant, might be significant. You need to pay attention on that when you're developing, when you're designing your code. But also, it must be possible that different processes might perform different kind of tasks, right? So MPI is going to be ideal for this kind of task parallelism, especially if it is like a coarse-grained task parallelism. If you think about OpenMP, it's like a more fine-grained task parallelism. When you do a parallelization of a for loop, right, you divide the tasks, and the task can be do some computation on some part of the array, and that could be a small, reasonably small array that will fill in the memory of your of your node. However, MPI, you can divide this array in a larger amount, so you distribute larger pieces of this array across several different compute nodes, right? So that's how MPI is ideal for. Also, I talk about task parallelism briefly here. That is basically dividing the work depending on the amount of on the task that you are doing, right? But you also have like data parallelism, that basically your data set is too big and cannot fit in one compute node alone, and then you need to break those data into different pieces and apply the same work on different pieces of the data on different nodes, right? So those are the two kinds of parallelisms. We're going to focus on task parallelisms. Most codes out there will apply a little bit of both, right? Sometimes task parallelism, sometimes data parallelism, sometimes both. For example, if you're doing a climate simulation, you might have a data set for the Earth, and you need to distribute that data on different compute nodes. So you have some sort of data parallelism. A data like the precipitation, temperature, pressure, wind speed, and so on, right? The historic data. And then also you need to compute your model on a grid, and the tasks will be divided also on different compute nodes, each piece of the grid covering some patch of the Earth, right? So it's both MPI might work both of them. We're going to focus today mostly on the task parallelism. So, okay, let's start with MPI basics. Okay, what is it, right? So it's an open standard library interface for message passing. So message passing is basically as I said, is the default way, is the most common way of exchanging data between two tasks between two nodes, right? Between two processes. And the idea of this standard came very long ago, like in the early 90s, because people were developing their codes, and each supercomputer, each vendor that would have a new supercomputer, they would develop a message passing interface with their own features. And so you have a lot of different vendors competing in the marketplace. And basically you need to write one code for each vendor. So it was very painful. People eventually, like the vendors and the developers and the scientists, they come together and they decided to come up with a standard for the interface and let the implementation be free to the vendor or for academics or whoever wants to do the implementation. But the interface should be standardized. And that's what they did with the first version and the later ones. Today, we are on the version 3.1. The 4.0 is under development with a new features that will make them hopefully fault tolerant to errors. And we're going to see how it goes. On Teach, on the SciNet clusters, right, you can find two kinds of implementation, the most common implementations. One is the OpenMPI. You basically load the module called OpenMPI. You can load with GCC or Intel compilers. And you have the version 3.1.1 that we're going to use on this lecture. We have another version 4 as well, but we're not going to use today. And we have MPICH2 that also went for several different names in the past, like MPICH3 and VAPICH2. And it's basically the version that the vendor, the Intel, the cluster vendor, packed for cluster. And then it is distributed as Intel MPI, and you just load that MPI implementation with module load Intel and Intel MPI. Okay, so the MPI is a library for message passing, so the compiler knows nothing about it. And all you have to do is to have several function calls inside your code, and then you link to that library. So for example, here you can see, you can see that any function from the MPI library, we start by prepended with MPI, and the first letter is uppercase letter of the function. And it can have also underscores. Okay, we're going to go into the details of how to implement MPI codes in a second. Also, the library provides what it looks like a compiler, like MPI-CC, MPI-F90, MPI-CXX for the C language, Fortran, and C++ language. But they are actually not compilers. They're just wrappers around the compiler that you're using. And I'm going to talk a little bit more about this in a moment. Okay, so what is the MPI library trying to do? It's trying to do the communication and the coordination between the tasks by sending and receiving messages, right? Each message involves a function call from each of the programs. So, okay, we're going to go into this detail in a second. And the MPI library provides three kinds of functionality. The first one is the pairwise communications via messages. As you're going to see later, the send and receive messages, how two tasks communicate with each other by that. The second one is by doing collective operations via messages, where every single task into the group of tasks that you are operating on send messages, participate in the communication, let's put it this way. And also it provides efficient routines for getting data from memory into messages and vice versa. So this is very good for doing parallel input-output. So parallel I/O, as it is called, and we have some course materials as well for MPI I/O, but we're not going to talk about this. This is very, very useful if your data is not laid out in a contiguous way in the memory. Let's say if you want to do some, if you want to save the data in a column-wise, but the data in memory is row-wise. So you could use these routines to create different groups, to create different data types, and lay down this data in a different way on the disk than it is on the memory. So we're not going to talk about this today, but just to let you know that this exists and it's very useful. Okay, so the first concept of MPI is message, right? What is a message and what it requires to send a message? So a message is basically a string of some data type, okay? So for example, here you have a count of some sort of data type that you need to declare as some sort of pre-existing MPI data type, or you can build your own, but we're not going to talk about this today as well. And in order to send this message, this message also can have an identification number that we call that a tag. So one node or one CPU, one task can send a message to the other one, and that message will have an identification so that this task here running on this CPU, on this node, know what to do with the particular task that you're receiving. Yes, and the message also needs to be actively received. You cannot just send it and let it go. You need to actively participate in the communication. So that means that there is a function call on the sender and a function call on the receiver. Okay. Yes, the types of MPI types that exist is basically characters, integers, floating numbers, but you can have any kind of type here that you might define. The user can define the types that they want. The size of the library. It's quite big nowadays, more than 200, maybe 1,000 functions, right? But we don't have too many concepts to deal with. So at the end of the day, we just have like 10 to 12 functions that we work with most of the time. The reason that we have so many is because we have different kind of features or applications or different kind of different ways to communicate. Maybe you wanted the communication to actually, you want a confirmation that your message was actually received, or maybe you don't mind that your message was received now, or maybe you want to use a buffer to send your message or not, right? And that proliferates the number of different functions that you can use, okay? But we're going to focus on MPI init, MPI com size, com rank, safe or secure or standard send, receive, and finalize. Brief word on the sign or how to access the teach code, the teach cluster. Basically, the teach cluster is the GPC system, the old GPC system. A couple of nodes of that was repurposed for the education and training, like we are doing today. For access, you just do SSH-y and use teach.signet.utoronto.ca. You go to your Scratch directory, and you're going to copy the course codes that I'm using today and that you're going to use to do your assignment. You just cp-r for recursive, signet course, summer school 2020 for MPI dot. And then you go there, and then you source the setup that I already put it there for you. It basically, it loads modules that we're going to use for today, okay? So running the computations, as Ramses mentioned, we have a scheduler that will manage the resources on the node as well. And then you have to submit a job script, a job with a job script. However, since we are doing this very quick kind of exercise, we don't need to submit a job script. You can use the srun that will allocate the resource for you and run the job all in one place, and then give the results back to you. I'm going to run some examples today. You don't need to necessarily follow right now. Oh yes, when you do this copy, you're going to see some files that are not allowed to be read, and those I made this on purpose because I don't want you to look at the solution. And please just take note of those file names and the paths, and then at the end of the course on Thursday, I will open them for reading, and then you can inspect the solution more closely, okay? Also, we have around 34 nodes. Some of them are just dormant. Let's say they are down, but as soon as you submit some jobs, they will wake up and then start running. But the cluster might not be so busy and should be able to run your srun command quite quickly. Sometimes you need to wait a little bit for others to finish running. But yes, let us know if it is too bad. But I checked the cluster just before this lecture and it was okay. Okay, so what are the simplest MPI example that you can think of is always the hello world program, right? You start by change to your MPI intro, and then you can compile and run this two versions of the hello world. One is the C version and the other one is the Fortran version. And I'm going to go into the details, what they are doing in a minute. And then, of course, once you source your setup, you source your setup, and that will load the modules that you're going to need. And then you run MPI F90 or MPI CC, that are the wrappers of the compilers, to produce the executables, the hello world F and the hello world C. And then once you have the executables, I mean, you pick one of them here, and then you can type it in srun -n n1 hello world, n equals 2 hello world, n equals to 8 hello world. That will run one instance, 2 and 8 respectively, of the same executable. Okay, let's go a little bit more into the details of what each piece of this puzzle is doing. So MPI-CC, MPI F90, as I said, they are not compilers, they are wrappers to compilers. And you can see what they're actually doing by just typing in, on the case of OpenMPI, the option -- show me. It's going to show what the compiler it was used and what the flags that it was used, right? And what are the options that it was used. So basically the wrapper here, excuse me, when you do MPI-CC hello world.c and -o and the name of the executable, the wrapper will call the GCC and keep the name of the source file and the output name of the executable, but we will add all the path searches for the header files and for the libraries file, for the search path for the libraries, for the header files, and what kind of libraries you're using, and all the information for the runtime or for the linker as well that you want to do it. So we don't want to be messing up with this whenever we compile our code with MPI. So this is very, very handy because it does this all for you. It wraps the compilation and the linkage for you, and then you don't need to worry about all these options, okay? Okay. What about MPI run, or also the modern version is called MPI exec, or srun does, right? It's going to launch any process and assign each MPI rank and starts the program, okay? So basically, it will get the executable that is on your disk, and then will load to memory on this node, on that node, on that node, on that node, okay? If it is a multi-node run, as I'm doing here, usually when you have only the MPI installed in your cluster, the runtime library will SSH to each node and launch the program there. Now here we have Slurm that does the resource management, and it will launch the jobs, the executables there for you, okay? So MPI run will only, if you type MPI run, it only run on the logging node, so it's not going to allocate the resources because this is the job of the scheduler, and the scheduler we are using is Slurm. srun, on the other hand, will allocate the resource and run the process that. And that's what we're going to use today. So just to be clear here, with this executable hello world, right? It is launched on each of these nodes, and it will give, yes. So Ramses. Yes, Ramses. Okay, I'm sorry. Oh, okay, I thought Ramses wants to interrupt. I'm sorry about that. So, okay, here we are launching the analogy, a good analogy of how this, what MPI is doing is basically the analogy of a company laying down the network on your neighborhood or your city, right? And that company will just lay the cables and connect the lines on your house and assign a number for each of them, and then you know each process will know what is the identification number. Each house is gonna know what is the identification number that it has, right? So that's the analogy. But in order to communicate, you need to connect the phone, and then you need to pick the phone and ask the operator a few questions that we're going to see in a moment. Okay. So how do I choose the number of processes? So usually, usually the number of processes is going to be equal to the number of the logical cores that you have in the code on your cluster. But that's not necessarily. If your cluster has hyper-threading, for example, there are hardware threads. So you can have multiple processes per core. Hyper-threading is not available on each cluster, but it is available on Niagara, that most of you have access as well. Suppose that you have an application that is memory hungry, that it's going to use more than 4 gigabytes per process. So you need to, you're going to leave some cores idle because you're going to need more memory per core than it is available. And suppose that you want your code to scale to a very large number of processes. And one way of doing this to decrease the overhead of MPI, as we are talking about like 60,000 core jobs, right, or MPI tasks, is to use a hybrid model with a threaded in MPI. And the way we do this with Slurm is basically, for example, let's say we're going to run one pure MPI with a 4-core node, right? You just ask for one node and the number of cores, 4 in this case. If you're using hyper-thread, for example, Niagara, you have 2 threads per physical core, then you would ask for 80 processes, 80 tasks. And if you have the memory hungry, if you have a process that requires 8 gigabytes per process, then you need to divide the number of cores that you are asking for by 2. So in this case, you would have only 20 cores to run your job. This is allowed on Niagara, okay, but only when you have when you are asking more memory per core than you have available. And if you're doing a hybrid run, you, for example, with 8 MPI processes or MPI tests with 5 threads each, then you have to add another option here. So you ask for the eight processes, and you tell that you want 5 CPUs per task. That is for short. The short is -C. Of course, in this session, you can omit the number of nodes. You're going to be always using one node, and you're going to use only the -n argument to require the number, to ask for the number of cores. Okay, MPI or MPI exec, MPI run or MPI exec, and srun, they can run any program. The program could be serial program, it could be a built-in command, it could be a parallel program. The MPI run will give all the information to that program about how to identify each other, how to find each other in order to communicate with each other, but it's not necessary. It's not necessarily a parallel program. So if I run, for example, host name on the login name, I'm going to see teach01. If I run MPI run on the login and ask for 2 cores, and the host name is going to run on 2 cores and will return me 2 instances of the host name output. That is going to be teach01 and teach01. And if I run with srun, then srun will look at the slum controller and ask, okay, do you have any resource available? Oh yes, I have the I have 2 cores for you on the teach02 node. So srun will go and launch 2 instances of host name on the teach02 node, and the output is going to be channeled back to your screen, and then we're going to see teach02 twice. Okay. Okay, so if I run srun and I ask for 4 cores of the real world C, I'm going to see 4 outputs here. And you see that the outputs, they are out of order. So the order is not guaranteed because it is a shared system. It's running an operating system that applies time sharing when it runs the processes, and each of them are not perfectly synchronized. So the order in which each task finishes is basically random, depending on how the OS is using the resource at the time and how the cluster is being used at the time. Of course, here in this code, we print to the standard output, a message saying what is my task ID, what is my task rank, and what is the size of that. But you could just get that information from the output by including a -- label option into srun, and then you can see which task actually output the message to the standard output. Okay, so in order to, so we see how we compile our code and how we look for the number of cores, but also when you are building your application, you can also build in parallel, right? Because sometimes your application has hundreds and hundreds of files, right? And the order in which you build them might not matter, right? So you can use an utility called make that is very good for this kind of for this kind of process. You just have to type make, and the make is going to look into a make file where you have listed all the rules to compile your code, all the source code, and how to link that to create an executable. Okay, and this utility allows you to do that in parallel by just typing the option -j. So if you type make, you're going to most probably just going to use just one core. Sorry, it's going to use just one core to compile all your code. If you type make -j2, it's going to use 2 cores to compile your code. And if you're going to type make -j, it's going to use all the cores available. Please don't do the -j on the login nodes. Be considerate with other people. You can use 4, maybe 6 or something like that, but not a very large number of cores, okay? So this is a way of also apply a parallelism when you're building your code. Okay, so what does the code do? Okay, let's look here. How do I instrument my code to call the MPI functions, right? Remember, the compiler doesn't know anything about MPI, anything about the library. Everything is in the library. So in order for you to do this communication, you need to call the library function, right? So in Fortran, the first thing that you need to do is to use the MPI modulo, where it's going to import the declarations of the MPI function calls, right? And then you have to use called MPI init for the initialization of the library. And at the end, you have the MPI finalize, where you close up and delete all the data structures defined before. And in between, you have MPI com size and com rank that I'm going to talk about in a moment. So remember, in the analogy of laying down phone lines in your city, right? And then you have MPI run does that for you. Now MPI init is basically the analogy of getting your phone set and just plug it in on the outlet. And this now gives you a connection with the library, with the runtime environment daemon about the information like your phone number or your area code, for example. Okay, so let's look at the C code and expand a little bit more on what the com size and com rank does. So the C code you have to include the header file for the MPI libraries, that is mpi.h. Here, you also call the MPI init, and you need, excuse me, and you need any argument for your code need to be passed for the MPI init, but be careful that it's not a guarantee that all instances of your MPI code will get all these arguments. Only the first instance might get. We can talk a little bit about this at the end. And you have to have the MPI finalized at the end. No MPI calls before MPI init, no MPI calls after MPI finalize. This is mandatory. Don't do anything before or after that will have undesirable and undefined behavior for your MPI application and might just crash. The MPI routines return an error code, but as I mentioned for the OpenMPI 4 standard, as I mentioned, OpenMPI, the current standard is not fault tolerant. So if there is an error, your application is going to hang or your application is going to crash, MPI will finalize your simulation. So there's nothing much that you can do with the error. So some people don't even use that error in the C code. But it is there because it's the fault tolerance feature is in development right now into the MPI standard. And of course, you have the communicator components. Let's talk a little bit about this. So the communicator is just a handle to a group of processes. And whenever the MPI starts, whenever your code starts, it's going to look at all the processes that you asked for, and that is going to be grouped in the MPI com mode communicator. So that's the default, the standard. Whenever you start, every single MPI code, when it starts running, will have the information about all the processes and grouped in this MPI com mode communicator. That is the default communicator that every single code has. If you want to know what is the rank of the task, right? You need to call MPI com rank, and that will do, and then we'll tell you what is the rank of the task. The rank of the task is just identification of the task. In task here, I'm using interchangeably with process. So it could be, it is a process or task. I like to call it task more often than process. So people understand clearly that I'm not talking about processor, that is the hardware, and I'm talking about a process. That is a software that the operating system is running on the memory. Right now, it's running on the CPU. So in order to avoid this confusion, I usually talk about task, MPI task. In rank, we'll give the rank of the task, so it's an ID of the task. In com size, it gives you the size of the communicator. So how many tasks I have on this process, or on my communicators. So I'm asking how many tasks I can communicate with in this communicator, okay? So basically that's how it is done. The MPI need, as I said, plug the phone. MPI com size, you pick up the phone and ask the operator, okay, what is the size, what is the area code, because my phone is in this area code. And MPI com rank, you ask, okay, operator, what is my phone number? Okay, and so that's the way that you are ready to start doing communications with other phone numbers, or in this case, with other MPI tasks in your computer, in your simulation, in your program. So a little bit about communication, a little bit more about communication. So it groups process in communicators, as I said. Each communicator has some size on the number of tasks, or if you think about this, the number of phone numbers in your city. Every task has a rank or an identification number that runs from 0 to size -1. And every task in your program belongs to MPI com word. So that's the default. When you start your MPI program, every task will be there, and that number will match the number of tasks or the number of processes that you ask to run your MPI code with. So here you see the MPI com word, the size is 4, so 0, 1, 2, 3, and the ranks from 0 to 3. Of course, you can create your own communicator over the same tasks. So you may break up the task into subgroups. Let's say you're doing some sort of like a multi-physics application, and one part of the code runs on all processes, and the other ones follow a particular communication pattern that doesn't need to run on all processes. You can run in a smaller number of processes, and you might need to reorder them for some reason, right? So you can do this. You can use MPI functions to create a new communicator. Let's say here is a new com with a smaller size 3, running from 0 to 2, right? And leaving one of the tasks out, okay? And as you can see, the labels, the ranks only make sense inside the communicator. So the rank 0 here is not necessarily the same as rank 0 in the MPI com role. So the ranks only make sense inside the communicators. Inside new com, that's the rank 0. Inside MPI com word, it would be equivalent to the rank 2, okay? So in a more advanced course, I'm going to teach you how to build new communicators, but that's for the future. So basically, the MPI communicator basics, you have a global communicator, as I said, MPI com word, and 2 functions to find out about what is the rank or your phone number, and what is the size. You can think about what is the area code, the number of phones that you're going to have on that area code. If you're following the analogy of laying down phone lines in your city or neighborhood or local area code. Any questions so far? I see that the message doesn't have many. Please feel free to ask questions. I might not be able to answer them right now, but Faye and Yohai might. And I'll just proceed. And then we can remember that on Wednesday and Thursday, you'll have more time to go back into the details that might not have been so clear right now as I speak. Okay, send and receive. So this is a kind of a pairwise communication. So far, we just have a code that says hello world, and basically it's just a code to put to let your program know what it can do, right? In terms of communication, how we can communicate with others. Now let's fix and see how we actually send these messages from one process, from one task to another. So the first code that I have here on the right, it is a code written in C, and basically what it's sending is sending a message from one task to another task. That's it. Okay, so let's read quickly this code. Rank and size are integers, send to and receive to are integers as well. They define which process or each task I'm sending the message to and which task I'm receiving the message from. Our tag I'm going to define as one because we're just sending one task and we don't need to identify several tasks coming from the same, we are just sending one message and we don't need to identify several messages coming from the same task, from the same process, right? So just keep it simple. I'm sending a message saying hello, and I'm gonna get the message, that's the receive buffer, and then I need an array of at least 6 characters, right? So 5 for hello and 1 for the no. And our status is just an MPI structure called MPI status that lets you know what is the tag of that message that was received and what is the count or how many elements were actually received, right? Then we call MPI init to initialize the library. We call comsize to get to know the size. The size and MPI rank to identify which process I am, okay? So remember, this code here, once I compile and execute, I'm gonna execute 2 instances of this code. And the runtime library will let this code know what is the rank that they are, right? Am I the rank 0? Then when this code is executing, the command is going to just enter in this block of statements here and start running this. Am I ranked 1? So when the code starts executing, it's going to jump this block and go into this else if because it's going to be true, and then start running this. So rank 0 is going to execute these statements. Rank 1 is going to execute these statements only. Okay, I hope this is clear. We can go back this later on as well. And so then you use MPI, I'm sending to 1, so the process or the task 1, and I'm receiving, and the process 1 is receiving from process 0, okay? So here we do a send message, so that's the array of the address of the array that I'm sending the message, and I have 6 elements, so it's a count of 6, and of the type MPI car. Remember that the MPI library doesn't know anything about the type or what is going on inside your code, right? So you need to explicitly let the MPI library know that what you're sending is a block of 6 characters, right? Send to is where you're sending to, in this case, the process 1. Our tag is the tag that will just identify your message, and the communicator MPI com, and then I send I tell what is the rank, right, that I'm sending the message to, and send a message, what is the message that I sent. And the same here for the receive. So I am getting the message. I can receive up to 6 characters, right? And receive from is, I'm receiving from the process 0. Our tag, identifying the tag that I'm supposed to receive. In this case, it's gonna be 1. MPI com is the communicator as well. And our status is going to tell me if it succeeded and where it actually came from and what is the tag and what is the size of that message that was received. And here I say got message from where, okay? In the Fortran version, you can do the same. I'm going to just emphasize or highlight one difference, that when you're sending a character, in Fortran, you're going to use the MPI type character. And when you're sending in C, you're, oops, where's my C version? Here. I'm sending MPI char, okay, MPI underscore char. Okay. So basically, that's a send and receive. That's the signature of the send and receive, the basic send and receive MPI calls, MPI functions. You send a pointer to the block of memory, and you tell the MPI how many elements you're going to have, and the type, the destination, the task destination, tag, and communicator. And the same here for the receive, the pointer where you're going to receive the message. It needs to allocate some number of some MPI type from the source that you are receiving the message. I am going to only, this guy will only deal with messages with the tag number set to tag, the communicator that you're doing this communication, and the status. The same idea for the Fortran, but the only change is that the functions in the C returns the arrow code, while in Fortran, when you call, the arrow code is returning as an argument of the function, of the function, of the subroutine. Okay, so let's take a look on a more complicated example. So what's the time? 1:30. I might have to speed up a little bit on the collectives later, but let's look at one example here now. So let's suppose that I want to send a message to the right, okay? You see that, oops, I'm sorry. Oops. Yeah. You see here that this process, they are not exactly, this task, they're not exactly the same in the sense that the tasks at the end, they are not going to be sending to the right because there's no right here, right? While the tasks in the middle will be receiving from the left and sending to the right. In order to help decrease the number of if statements, you see that here we have an if statement for two processes, right? So sometimes this can become quite nitty. And in order to help decreasing the number of if statements, MPI defines some special values for the source or for the destination for some kind of for some tasks, for some source and destination tasks. One of them is called MPI proc no. That is basically, it pretends that you are sending a message there, but it's not sending anywhere, okay? And the other one is the MPI any source. That is basically a wildcard that will match any source that you are receiving. And that's one of the reasons why you have that status object or status structure in the receive function call, is to identify from where it's coming from, essentially. And we are going to use on the next code the MPI proc no. So for example, if I want to send right and receive left, right, I do the following. Okay, start MPI gets the rank, right? If I'm left, I just say, oh, rank -1 is going to be my left. So the left of 1 is going to be 0, right? However, for 0, the left is going to be MPI proc no, because you don't have any process there, right? The same for the process 2. The process at right is going to be your rank +1. However, if I get to the process 2 here, the right is going to be MPI proc no, because I don't have any process to the right, okay? And here the message that I'm sending is rank squared, and the message that I'm receiving is -999. And the idea is just for you to spot which process is not receiving anything. So if I go and type it in the message, call the MPI send, and send a message 1 double to the right, okay? And then I receive a message on the receive buffer, one double to the left, okay? And then output to the screen which message each one is receiving. So if I run this code, I compile with make, second message C, and then I run with 3, I can see that the process 2 sent 4 and got 1 from the left. The process 0 sent 0 and got nothing, so that's the minus 999. And the process 1 sent 1 to the right and got 0 left from the process 0. And it can run with any number of processes you can play with. Okay. Okay, now suppose that I have periodic boundary conditions. Let's say I'm doing some computation on a ring, and the grid just needs to be in a ring format, and then they will communicate with each other. And when you reach the extremes of the processes, right, of the ranks of the processes, then you need the last process needs to communicate with the first one. So how do we do this? Well, we basically apply what is called periodic boundary condition. The process at left is going to be actually the last process. So the left is going to be size minus 1. And the process on the right is going to be actually, that's the process right is also rank plus 1. That's fine. But if I reach the right greater than the size, if I in my loop I reach the latest point of the task, then I assign the right to be the 0 processor. I do the same sort of send and receive messages. And if I compile and run this code here, what you're going to see is that the code is just hanging there and do basically nothing. So what's going on? This is a classical parallel bug called deadlock. Essentially, all processes are basically just sending a message, but nobody's listening, nobody's receiving the message. In the phone analogy, everybody's dialing, but nobody's picking up the phone to actually answer the call. So whenever you have this kind of a closed circle, closed loop, you have a very big risk of having a deadlock. Most of the time, you're going to have a deadlock. All the processes are basically sitting there idling and waiting for the messages to arrive, and the messages never arrives because nobody is actually listening or receiving. Sorry, everybody's sending the message, but the message is not going to be received because nobody's actually listening or waiting for receiving. So that's the MPI big lesson number 1. All sends and receives must be paired at the time of the sending. Okay, so what do I mean by that? Let's see how we can fix how we can break this deadlock. One way of breaking this deadlock is by splitting who is sending and who is receiving the message. For example, we could do an even-odd solution where the evens will send while the odds are receiving. And then the next step, the odds are going to be sending and the evens are going to be receiving. Okay, so this is one way of breaking the deadlock, and I'm going to show you in a moment. I'll let you work this example with odd number of processes and answer these questions here. We can come back to them later on. So basically what you're sending here, the modification in the code is quite simple. So basically, first you decide if you're even or if you're odd, right? And if you're even, you're going to send a message, 1 double to the right. And if you're odd, you're going to be receiving a message, 1 double from the left. So see, at the time of sending, this MPI receive here is paired with this MPI send here. Once this is received, this message is received, this code here returns the command to the calling function, and then the next step is going to be MPI receive. It's going to wait to receive a message. And the same thing here for the odd processes. It's going to finish receiving the message and go to the next statement, and now it's going to send the message. So the send function call is paired with the receive function call on the even process. Okay? And if you run this, now you don't have a deadlock anymore. Okay. So MPI library provides you a function call that combines both in one. It's excellent to use the send receive because in this way you avoid having to come up with solutions for any kind of problem to make sure that the send and receive are paired, right? In avoiding deadlocks. So MPI send receive basically put them together in one command, in one line. So it is a blocking send receive, but they are guaranteed to match. So the calling function signature is similar to the send and the receive. So the send side, you're going to have send pointer buffer that will send a block of count MPI type to the destination with a particular tag. And the receive is going to receive, you're going to show, you're going to define, you're going to send, you're going to receive the pointer for the buffer that you're receiving, a block of count MPI type from the source with a particular tag inside the communicator, and that's your MPI status. Okay, it automatically pairs, sends, and receives. You can have two types of, yes, you can have two sets of tags, one for receive, one for send, one for receive, and types and counts. For example, if you want to do, let's say you're sending 10 doubles, that is a row in a matrix, and then you might receive one MPI row or column data type, right? So this doesn't need to agree. It just needs to agree in terms of what is laid down in the memory. We can talk about this more later. And so here's the code, and if you run it, you get it the same sort of answer. Okay, so there are different kinds of send. What we used is the standard synchronous send. It's a blocking operation. It's not return the command to the calling function before the data is actually received on the other side. So that's the safe and the standard way to do. We're going to use this in this class. We have also the buffered send that is guaranteed to be asynchronous. The routines return before the message is delivered. Basically, the system copies the data into a buffer and sends it. It is a little bit risky. You can fail sometimes if the buffer is not big enough or if the buffer is full. So we're not going to be using that. And you have the usual standard send, the first send that was implemented both as synchronous and asynchronous, depending on the size of the message. That caused a lot of confusion, and it's not used anymore. And of course, we have a non-blocking kind of send that is called MPI send, that we might talk about this on Thursday. Okay, collectives. So far, all the communications that we have was pointwise between two pairs of tasks, between two pairs of processes, right? Now we're going to talk about collective communication patterns where every single process in the communicator participates of the communication. So for example, if you have a reduction where you want to compute the minimum, the mean and the maximum of random numbers going from -1 to 0, right? And how do I use MPI to parallelize and speed up this kind of computation? So the reduction is basically a transformation into the data from a large data set to a small data set, applying some sort of operation into the elements of the data set. So you could use partial results on each node. So you do the minimum, min, max on each node and send the results on node 0, where it's going to compute the min, and max for the global, for all the processes, right? So briefly, I'm running out of time. So just to mention quickly what this code is doing, right? One way of doing this, right? So basically here, After initialize the MPI and know your size and rank, you basically create a new data set, and you fill the data with random numbers here between -1 and 1, right? And then you compute the minimum of that data set and store this array element, and the maximum and the mean. There is no average to do this average. To do this, you need to basically do the sum first and then divide by the number of elements later on. And then if you're not the rank 0 MPI, you're going to be sending what is the computation of the minimum, maximum, and mean that you have done so far to the process 0. And if you're the process 0, the task 0, you're going to be receiving from each one of the other processes, right? An array of 3 doubles, and then you do the computation, computing the minimum, the maximum. Those are going to be the minimum and the maximum that you have done for all the processes, right? You receive the minimum, maximum, in the sum from each of the processes, and then you see what is the minimum and the maximum with respect to your local minimum and maximum, right? And then you compute the mean by dividing by the number of processes, the sum by the number of processes, and print to the string, okay? So this is interesting. It solves the problem, but there is a fundamental problem doing this, because every single process is sent to one process here, and the process will have to do the sum on its own. And it's very inefficient because basically you're serializing the computation of this sum. And the cost is going to be proportional to the number of processes that I have here, right? As you increase the number of processes, the sum that one process needs to perform is going to be larger. So it's very inefficient. A better way of doing this is by doing the sums in terms of pairs, right? So the process 1 and 2 do the sum as the process 1 sends to 2, and the 2 will send to 4 and do the sum there as well. By doing this kind of tree, this hierarchy of tree, you can speed up the total cost. So you can speed up the computation. Now it follows a log 2 of the number of processes, right? And on top of that, you can exploit, exploit some network graphics kind of computation abilities to do this, to perform this computation during the communication. It works on a variety of operations like the sum, the product, the minimum, and the maximum, okay? You might want to be tempted to do this kind of programming, but it's going to be very complicated to do that. And MPI already knows how to do that. All we need to do is call a function called MPI reduce. And basically, MPI reduce will do the reduction of the data that you have, the send on the send buffer. That is going to be a count of MPI type again. And it's going to do the reduction and store on the receive buffer, okay? And then it's going to use MPI op, that can be any of the operators like sum, prod, min, and max. And then we're going to send that solution to the root processor, the root process on the communicator. The root process also usually is the process 0. That is the one that exists, that is guaranteed to exist always, right? And if you want to do, if you want all the process to know that result, you can use the MPI all reduce. That basically will do this reduction and broadcast to all other processes. Okay, so then it becomes very simple to do. It's just a 3 call function calls to MPI all reduce. In this case, I can have I can reduce the minimum and save on this is the send, right? I can send the result of my local minimum to the global, to store the global max and to the minimum, and then basically output the result. Okay, so the collective operation, reduction is an example of collective operation. as opposed to the point-to-point or pairwise message. All processes need to participate, and you don't need to know necessarily what is under the hood. Usually is quite optimized and using modern algorithms and take advantage of the hardware, network card, computation capabilities as well, so you can do that on the fly on the communication. We have other kinds of MPI collectors, such as the broadcast. Let's say the process 0 reads the parameter for the parameter files for your code, and then it just broadcasts the same data to all other processes in the communicator, including itself, right? We have MPI scatter that basically split the data and then scatter the data into the other processes. We have MPI gather that basically does the opposite and store in a larger array, right? So this is a kind of what OpenMP is sort of doing as well. I mean, splitting the data to be computed on each core, right? But the difference here that we are doing this explicitly and sending to maybe to another node for another task. We have file I/O that we're not going to talk about today, and barriers that we should not use. I'm going to talk a little bit quickly. And finally, we have all-to-all. That is basically a combination of scatter and gather, and it's a n-squared kind of order of computation. So it's not, if you can avoid, please avoid, because it's very costly. So if you see the broadcast, right, you broadcast a message from one process to each other. The signature is basically you have the buffer, the pointer to the data that you're going to send or receive, the number of elements in the buffer, the MPI type. So you see that all the MPI functions sort of follow the same kind of signature, right? It's always like a count, MPI type. If you need to know a destination, it's there. You always need to know the communicator. And if there is a buffer, a pointer to a buffer, it is always there, right? So you see the scatter and the gather also has the same kind of, the same exact signature, but it's just that the send buffer, the size of the send buffer might be a little bit different. Or let's say the scatter, you are sending data from the root, while the gather, you're receiving data from the root, okay? You're receiving data on the root, sorry, from all the processes in the group. So the first problem that I wanted to do is to take a look on how the scatter code works and copy the scatter.c to gather.c and reverse the process. We can talk about this more tomorrow if you want. I can look at the scatter code with you, and then we can have more time to discuss this. Okay. This exercise is known. It's optional. I wanted to focus on the latest one that I'm going to introduce right now. Okay. Okay. Blocks, barriers. It's a good. It's good to use only when you are developing your code, only when you are debugging your code, because barriers block the advance of all the tasks. No task can go beyond the barrier. And so if you're trying to build like a load balancer for your code, it's good, because then you can know when each of them are getting there, and then you can find a way of balance the load. But in production code, please do not use them, because most of the time they are just degrade the performance of your code. All-to-all is basically a scatter and a gather put together. Basically, each process split the data that wants to send to all the other processes. Okay, and this data on all the other processes are going to be different, so they have to split that data as well and send to all the other processes. One kind of application that this kind of things is the Fourier transform. If you don't do fast Fourier transform, you end up having to do this kind of transposition, and it is very expensive. As I said, it's like it goes as order n2, n squared. Okay, you cannot if you can avoid at all costs. Okay, so that's it in terms of basics MPI that most of you need to know. I might add on Thursday a little bit more about the non-blocking communication patterns and non-block communication functions. But right now, I want to introduce a scientific MPI example that you can apply this, what you have learned today. So consider the diffusion equation with an explicit finite difference time marching method, right? Imagine that the problem is too large to fit in the memory of your code, of your node. So we need to do what is called the domain decomposition or use MPI. So basically, you have a partial differential equation, like the diffusion equation here, where the time derivative of the temperature, how the temperature changes with time, is going to be proportional to the Laplacian of the temperature along the rod. Let's say that I'm computing the heat transfer along a rod, right, one dimensional. And then this Laplacian is basically telling you how that point deviates from the average. It is colder, it is hotter. If it is too hot or too cold compared to the point where I'm computing the Laplacian is going to be, if the neighbors are too hot or too cold, right, the average is going to be higher. Then what is the value of the temperature at that point? And the Laplacian is going to be large. So that means that the temperature should change quite quickly, should decrease quite quickly there. So basically, that's the physical setup of the diffusion equation, okay? In order to compute that, in order to compute this diffusion equation on a supercomputer, you need first to find a way to represent the derivatives in a grid, right? So the function we already know, the continuous function we already know. You can all know the function at this point, the function at that point, and the function at that point, and now you have the values of the function in a discrete grid. But the values of the derivatives, you can use the Taylor expansion in order to discretize the derivatives. For example, here you're using the temperature at the point I, the temperature at the point I plus 1, and the temperature at the left neighbor here, okay? And this is represented by what is called a tensor. That is basically a rule on how I compute the derivatives on the point I, on the point of the grid, okay? I can have larger tensors to have more accurate answers, as you can work out what is the order of the error of these approximations, okay? So basically, that's a basic introduction. And to solve this equation along the rod, all I have to do is to slide this extension along the grid of these cells represented in blue here, okay? So the diffusion equation, when I discretize the diffusion equation, I end up in one dimension with this kind of discretization, one possible kind of discretization, where the temperature at the point I, at the time n, the time step n, and the temperature at the point I and the time step, the previous time step, okay? And the partial derivative, the same thing, using this kind of extension. In 2D, I will have the extensions on each direction, and the rule to compute the derivative on one point will change slightly, as you can see from the weights of the extension. I don't need to go into the details here. The computation becomes a little bit more elaborate, but it's the same idea applied in different directions. Okay, so as I said, to compute the differential equation, I need to slide the stencil along the grid of cells, right? But how do I do when I reach a boundary, right? One way of doing that is by introducing what is called a guard cell on each side and just apply a boundary condition there, such that when you compute the derivative on the first cell, you have the value for that boundary condition there, okay? And then when you do the loop, you loop from this cell until the number of, you loop only on the interior cells that you have. So you basically add just 2 cells to help you with the computation of the derivatives, of the discrete derivatives on the grid. In 2D, you do the same thing. You have your original domain. If I want to compute the derivative here or the derivative on this corner here, I'll need values of the function also on these external guard cells. So you basically have this kind of halo around the domain. So I'll have to extend a little bit. I think we are almost done, but I might need 10 minutes of your time to finish up this. So the main idea of it's very common in scientific applications, like in physics and engineering, to do this kind of domain decomposition. It's an approach that you basically divide the physical domain in several different pieces and let each process, each compute node to deal with that part of the domain. For example, if you're designing an airplane that you want to make it quiet or more efficient or more fuel efficient, you need to first do the simulation. And to do the simulation is very expensive. The whole representation of the airplane does not fit in the memory of one compute node. So you need to break up and send each part to each compute node to do the computation on their own. Or you might have like a particle in different domains, right? Some sort of particle simulations. Or maybe you're doing some sort of a climate computation and you need data and you need to divide the domain on several different patches of the world, right? Of course, you need to be very careful with the communication. You want to have your data as local as possible so that you have less communication between the process to do. Or for example, you can have like a domain decomposition that is dynamic, right? It changes as the features of your solution shows up in order to balance the work that needs to be done, as for example, in this simulation of 2 galaxies colliding here. So the main idea here is that you want to maintain data locality so you minimize the communication between the nodes. Communication, data movement is expensive. Okay. How do we use the guard cells to do this kind of change? So basically, you divide the domain, so from 1 to 5, and from 6 to 10, okay? And now you want to do a communication between them. You basically add the 2 guard cells as you would to do the computation in one domain only, right? However, this, you apply the boundary condition, but this guard cell here, you get the data from your neighbor that has done the computation of the data there. That data actually belongs to your neighbor. So you need to send a message, your neighbors need to send a message to you. And in the same way, you need to send a message to the guard cell of your neighbor. Okay? So given the little time that I have here, don't worry, tomorrow I'm going to go back from this exchange of data here to make it more clear. I'm just going to finish talking about the 2D and present the code that I want you to do. So how do I divide the work in a 2D grid, for example? I would have more freedom to do that, right? So for example, in this here would be more efficient, and end up being more faster because I have blocks of the data, and the surface between the 2 processes are going to be smaller. So the less communication, have 18 edges. You could imagine sending 18 doubles between the nodes. So it's going to be faster to compute and faster to run than in this case here, that it's analogous to 1D and has, but it has more communication surface. So in your production code, you want to minimize the ratio of the surface to the volume of the number of grids, okay? So if you do the serial code decomposition, it's very common to find this on the web. And basically, it's like doing the serial one that we did. It's like doing the 1D before, but in this case, we just we just instead of sending data one side to the other, you just send data up and down. So for example, the data here on yellow, you need to be sent to these guard cells here. And this process here needs to send the data in green to this guard cell here, such that the computation of the derivatives can be performed there. Okay, it's very similar to 1D. Okay, finally, I apologize to have to speed up on the last few slides. I might have to return tomorrow and go slow again so you can understand better. This is the hands-on 1D MPI diffusion equation. You're going to get the serial code on this directory. You go to the diffusion directory. You're going to compile diffusion.c, and then you run it. Your task is just to parallelize that version. I think I have it ready here. So if I do the diffusion, I don't know if you're going to be able to see that well. Oops. As I run the diffusion equation, you see the temperature just slowing down, right? Let me try again. I don't know if you can notice that, but that's just one run of the diffusion equation, one-dimensional diffusion equation, the serial version that is doing all the computation of what I just said to you, and I will repeat tomorrow so you refresh your memory and make it clear. Okay, so basically you're going to copy this, either the C or the Fortran version, to the diffusion C-MPI. You're going to make MPI version of that, build that, and test 1 to 8 processes and see if it works. Okay, so how I suggest you to do that. First, switch off the graphics. You see that the graphics that I showed, it's nice, but it might not work well, and it's going to slow you down. So you just use gplot, use pgplot. You just set to nothing in the make file. Then you're going to add standard MPI calls like the init, finalize, comsize, comrank. So each process has the opportunity to know which process they are. And then you're going to figure out how many points each process is responsible for. For example, the total number of points over the size, right, of the number of tests that you have. Then you have to figure out who are the neighbors. And then you start at 1 and end at the number of total points. So that's how the loop is going to go. You need to figure out that. And at the end of the step, you have to exchange guard cells using send receive and get the total error. Okay, we're going to return to this problem tomorrow. So I can talk a little bit slower and answer your questions. Please review these slides today. Go over the codes that I have to go over today. I have to rush a little bit, and I apologize about that. The first change of format. So, but I really feel strongly that you should have all the basics of MPI, and these are the basics of MPI. I hope it was reasonably clear. And so we can talk about this tomorrow, about the steps of tomorrow again. Oops. Yeah. Yes, and my slides have some MPI summary of the C syntax and Fortran syntax. And I have a list of some good reference that you could take a look. Remember that every MPI command, every MPI function also has MUN pages. You can check it out, the MUN pages, and they will be helpful to answer your questions as well. So I think I'm going to open for questions. I apologize for the speed up at the end, but I hope you got the main idea. Do you guys have any questions? Please let me know. Ask questions in the forum. I will monitor the forum. And tomorrow I will go back to this diffusion equation. So we go a little bit slower, and I can get you the main idea of what I want you to do. You can go into the serial code as well, so you have a better idea. And I'll be here to answer your questions tomorrow. Remember that the attendance code is 10. Okay? So, thank you.